Today is our great pleasure to invite Dr. Visweshwar Marthi from National Center for Radio Astrophysics in India to present a talk to us. The title is Pulsars and FRBs with the GMRT. And before starting the talk, I would like to introduce Visweshwar a bit. So Visweshwar has a unique career path in astrophysics. He did his master in communication system in engineering. And after that, he worked in the IT companies for a while before starting his PhD in NCRA for astrophysics. And during his PhD, he works on the OT radio telescope, focusing on methods and the challenges for 21 centimeter detection for the high redshift. And after his PhD, he moved to CETA in Toronto as a postdoc layer and works on the scintillometry and the simulations. And he returned to NCRA in 2019. And his current interests including the interstellar scintillation and the FRBs, especially using FRB to study the host galaxy and Milky Way interstellar medium. And he is working on instrumentation and for the VLBI in the India. And now he is a tenure faculty in the NCRA. So let's welcome him, and please feel free to start. Thank you.
Thank you, Shushan. Thank you for the introduction. And hello, everyone. Good afternoon from India. It's still a little before afternoon here, but the idiosyncrasies of doing talks online means that we are sitting across different time zones. It's actually brought the community a lot closer. So there are also silver linings to talk about when we talk about the pandemic. So it's my pleasure and it's an honor to give a colloquium at ASIAA. And so today I thought I'll talk a little bit about focusing a little bit on my work that I have done, and a little forward-looking as well. My interests are mainly pulsars and fast radio bursts. And as Shushan just mentioned, I'm also interested in developing instrumentation for VLBI, where my own science interests actually have a fairly substantial VLBI component in the near future. So without much ado, I'll just introduce the fact that, just to mention the fact that the work that I'm going to present is actually in collaboration with a large number of people, both within NCRA and, of course, across the world, many of whom I've actually had the pleasure of working with in CETA. And I still continue to work with some of them in Max Planck Bonn and CETA as well. So, the talk itself is actually set in 3 parts. So I'll first talk a little bit about the pulsar work that I've done, and then talk a little bit about how the GMRT has actually aided in some FRB observations and some science that we've done with the GMRT on FRBs. And in the third part, I'll also talk a little bit about my own efforts at VLBI instrumentation. And I understand that there's a lot of VLBI expertise in the institute in Taipei. So this is the broad outline of my talk in 3 parts. And so without much ado, I'll just get on with the first part of my talk, which is about pulsars. And of course, as astrophysicists, we're all very familiar with what pulsars are. And I don't have to really give a very basic introduction to pulsars, but I think it's important to appreciate the fact that particularly from my point of view, pulsars, the way we use pulsars, for my science interests, I see pulsars as excellent probes of the interstellar medium, because pulsars are compact objects. They're unresolved at all wavelengths, and therefore you can use them as excellent probes to study the medium that intervenes between us and the pulsars. And so the next few slides that I'm going to present is mostly about the work that I've done with a very interesting pulsar B1508+55 using the GMRT. And you will already see here that there's also a bit of pseudo VLBI component in this work. But let me just do the introductions now. So, so when I said that pulsars are actually very useful probes for studying the interstellar medium, what we mean is that there are many effects that the interstellar medium imprints on the incoming wave field. And there are many effects like dispersion, scintillation, and scattering. And my own interest mainly is on scintillation and scattering. And just to give an example of what scintillation can do to the pulsar signal, what you have on the screen is something called a dynamic spectrum, which is the received wave field. It's not, it's the received intensity as a function of time and frequency. And the received intensity is nothing but the square modulus of the wave field, the electric field. Now, so this is the dynamic spectrum. This is an example dynamic spectrum of a very well-known and intriguing pulsar, intriguing from the point of view of scintillation, of a pulsar called 1133 plus 16. It is well studied, and it's also it's a favorite pulsar among those who study scintillation. So the features that you see in the dynamic spectrum, they look like some sort of wave patterns, and they arise due to this phenomenon called interstellar scintillation. And that's because there's multipath propagation. Waves coming from slightly different directions actually interfere at the observer, causing constructive and destructive interference, and that's what gives rise to these patterns. And so it's a multipath propagation effect, and this effect itself can be used to study the medium, although it is in some sense it is a nuisance for people who do, for example, timing at low frequencies. This is actually a nuisance, but if you look at it the other way, people who are interested in the interstellar medium and propagation and wave propagation and things like that actually look at it with a lot of, I mean, through a positive perspective. So, so that's just a zoo of scintillation dynamic spectra. You can see there's a large variety in the features. They look very different. Sometimes even from the same pulsar, they look very different at different frequencies, at different times. So it's a very rich phenomenon. There's a lot of variety there. And so in general, you look at scintillation as something to do with scattering, and it's actually not at all. The two are not completely disjoint. I mean, scattering and scintillation sort of sometimes go together hand in hand. So the basic picture is that there is a compact object like a pulsar, which is also moving in space, and then it's giving out radiation, and radiation is passing through. So this is an idealized model. So there's a plasma, there's a slab of plasma, which is this is called a thin screen approximation. So the dimension of the screen along the direction of propagation is actually negligible compared to the distance to the pulsar itself. That's the thin screen approximation. So you have a slab of material which has some turbulence, and that causes the wave fronts to be distorted because they impart slightly different phases at different points. And because of the distortion, the wave front actually travels slightly different. So they appear to come from slightly different directions, and therefore they cause an interference pattern. And the Earth is actually moving across this interference pattern. And this particular picture is called the frozen screen turbulence model. So this is an approximation. It's a useful approximation to understand how scintillation is caused and how we are able to observe it. So, so I showed you examples of dynamic spectra, which are still seen in the top row of this picture. But what you see at the bottom row is the two-dimensional Fourier transform, or what is called the power spectrum, as many people would prefer to call it. It's the power spectrum of the dynamic spectrum. And what this power spectrum does is actually it gives you the autoconvolution of the electric wave field that is received at the observer. So you can see all these parabolic features. It is conventional to show what you see at the bottom. The power spectrum is also called the secondary spectrum, and right now the convention is to actually show the power spectrum with a 90-degree rotation. So this was in the early years when the parabolic arcs were just discovered in 2001 by Dan Steinbring. This was the convention to show, because the way the dynamic spectrum was plotted, was with the frequency on the y-axis. So, so it's just a Fourier conjugate axes which are correspondingly plotted. So you see this parabolic effect because of the fact that the angle, the delay with which a wavefront is received as a function of angle is parabolic. It's a very simple geometric picture, and therefore you get this this kind of parabolic arc. But also notice that there's a variety in the way the parabolic arcs look. So, for example, different pulsars show slightly different looking parabolae. Some of them look very clean, and some of them look fuzzy. And sometimes you often see, for example, in the first one and the last one, it looks like there are multiple parabolic arcs. So all this is now sort of reasonably well understood. So I'll, instead of going into the details, just flash another example of what is quite familiar to people who do scintillation. And these are called reverse or inverted arclets. So you have a main parabolic arc, a forward arc, and then you have a reverse arc, a string of reverse arclets with the same curvature. And this is also understood. So these are all understood in terms of whether the scattering that causes the scintillation is strong or weak. And so it has its own, there are advantages to both having inverted arclets, or, the case where on the top right, for example, it's just a simple clear plane arc. So there are ways of inferring the properties of the scattering based on how these parabolic arcs look. So so that was just the introduction to dynamic spectra and what the secondary spectra look like. And now I'm just going to digress very briefly, because this is just a jump from scintillation and dynamic spectra. Just a brief digression to the Giant Metrewave Radio Telescope, which is the telescope that is operated by NCRA. It's a well-known international facility. It was conceived and designed in the early 90s, and designed primarily as an interferometer. So it has a Y-shaped geometry. I mean, the array is shaped like Y, and it has these 3 arms where each arm has about 5 to 6 antennas, and then there's also a central condensation with about 15 antennas. And the Y arms actually aid in getting high resolution because they give you the longer baselines, whereas the central antennas are clustered together within the 1 square kilometer. So there are lots of, you get high sensitivity at these short baselines, and that improves your sensitivity to low surface brightness features. So in terms of if you talk about an interferometer, this is a fantastic instrument because it's both sensitive to large and small scale emission on the sky, and it can be used in very flexible ways to optimize your science observation. Now, as I said, it was designed in the early 90s and operationalized in the year 2000. The legacy GMRT had about 16 to 32 megahertz of bandwidth, and subsequently there was also a software backend which was designed, and that gave you about slightly similar bandwidths. I would say 16.66 and about 33 megahertz of bandwidth, but the backend was substantially more advanced. And now what we have is called the upgraded GMRT, which gives you an order of magnitude larger bandwidths, instantaneous bandwidth. So you get either 200 or 400 megahertz, depending on which band you're able to observe. And it also gives you nearly, because of the wide instantaneous bandwidths, you can also observe nearly seamlessly between 140 and 1460 megahertz, there except a few small gaps in between. So it's a fantastic low frequency instrument, very sensitive, very versatile. And so with this just short introduction to the GMRT, I'll tell you how the GMRT was used in a particular observation, along with what is called the Algonquin Radio Telescope. The surprising fact, or rather the pleasant surprise here, is that the GMRT dish, each of them is about 45 meter in diameter. And the Algonquin dish is also exactly 46 meter in diameter, so similar. So in that sense, the dish size is well matched, so the beam size is also well matched. That itself is not critical for what I'm going to talk about, but I'll just talk about this interesting experiment that we did, which is observing this pulsar 1508 plus 55 with the GMRT and ARO. So this particular baseline is 10,000 kilometers, and this pulsar is high declination pulsar, and this is circumpolar at Algonquin. And therefore, the only constraint was how we could observe it with the GMRT. Okay, so so we observed this pulsar for scintillation on 6th of August and 12th of August. What I'm showing you here is only the dynamic spectrum from one day, not the second day, the first day. And you can see the GMRT dynamic spectrum and the ARO dynamic spectrum. The GMRT dynamic spectrum looks so clean because of the higher signal-to-noise ratio, because a lot of dishes have been combined. We have combined the signals from 15 dishes, whereas the ARO is only one, but still you can see some features that look common. And what you see here in the middle is the difference dynamic spectrum between the two stations. Now, the purpose of doing this experiment is to actually measure the scintillation dynamic spectrum and to measure the arrival time or the difference in the arrival time of the scintillation at the two stations. The idea was actually to do this on 2 different days because we don't have a third baseline. We don't have a second baseline, I beg your pardon. We have only one baseline. And the only way we could actually measure a 2D velocity vector was to separate the observations by 6 hours in local sidereal time. So they would give you a pair of orthogonal baselines. And we had to do this reasonably close so that the scintillation was not dramatically different on the 2 days. And on the second day, for some reason, the ARO failed and we could not use those observations. But the idea is that we use the difference, the time of arrival of the scintillation at the two stations to infer and study about the scattering screens. So, so what you see on the right here is actually how, for example, this is just a cartoon, of course, how the baseline would look from the pulsar 1508 plus 55. And what you see here is the GMRT, and this end is Algonquin. So that's a fairly long baseline. It's a 10,000 kilometer baseline. So just a quick slide on the results. On the top left, you see the secondary spectrum, and I've already introduced the secondary spectrum, although this looks very different from what I already showed for examples of secondary spectra. And that's the thing about secondary spectra. They're all unique, and you can have very different, it depends on the picture. The scattering picture could be very different for different pulsars. And here in this particular pulsar, it's a very intriguing and interesting case. And what you see here is a secondary spectrum on 2 different days. And you can already see that some features which are actually marked in this black, green, and blue dots have actually moved. 6 days later, they have moved. And it's really telling you that features in the ISM are actually moving relative to the pulsar. And what we did is we took the secondary spectrum at GMRT and also at the secondary spectrum at ARO. The secondary spectrum at ARO is very poor signal-to-noise ratio. But even before going to the secondary spectrum, when you just take a Fourier transform of the dynamic spectrum, it's going to give you a complex quantity. And when you cross-multiply the two complex conjugates, so you take the complex conjugate of the ARO Fourier transform and multiply it with the GMRT's scintillation dynamic spectrum's Fourier transform, and that will give you a complex quantity. And this is typically how interferometry is done, for example. You take the voltage from one, voltage from another, and cross-multiply the complex conjugate quantities. So that would give you a phase, and that phase is actually nothing but the manifestation of the delay in the arrival of the scintillation. And that scintillation can also be measured. I mean, this is just one way of measuring it. This is a cleaner way of measuring it because one can actually measure the phase gradient, and you can also measure it through a shift in the peak of the cross correlation, although I'm not showing that plot here. So there are multiple ways of measuring it. This is just a clean way of measuring it because this just gives you better signal to noise. It's a much nicer measurement. And so this gradient actually translates to a scintillation delay of 45 seconds, which means that the scintillation pattern which arrives at one of the telescopes arrives 45 seconds later at the other telescope. So it takes 45 seconds to traverse this 10,000 kilometer baseline, and you can immediately convert this to some kind of a scintillation speed. And that turns out to be about 220 kilometers per second. And we also measure cross-correlation coefficient of 0.22, which means 20% of what is seen at one station is only 20% or 22% of what is seen in one station is seen at the other station. They're not exactly identical. And the scintillation timescale, rather, is nowhere close to 45 seconds. It's about 3 times more. It's about 140 seconds, plus minus 5 seconds. And we also measure an arc curvature, which itself is used for a different purpose here, but just for completeness, I'm just showing the measurements and the results. So what we infer from these measurements is that there are 2 screens. One is, of course, it was already known that there is a screen at 125 parsec. And that is what we actually see as the secondary spectrum here. Besides, there is also another screen which we don't see in the secondary spectrum of the GMRT, but that is what is actually detected on the baseline. And these things can happen with scintillation. When you actually look at it at different frequencies, you could see a completely different scattering picture on the sky. And that also goes for baselines, because you're actually, with a baseline, you're resolving structures on the sky, and there's no guarantee that what you see with a single dish is going to be seen with a longish baseline. So what we see is that we infer that there are two screens, and one of the screens, it was known to be at 125 parsec, and we have verified that this, whatever we see at the GMRT secondary spectrum, is caused by the 125 parsec screen. And the apparent scintillation speed, which is the 220 kilometers per second that we measure on the baseline, is actually a result of an enhancement, because the actual speed is only 200 kilometers per second. And that's because the baseline is actually oriented at a slight angle with respect to the motion of the pulsar. The pulsar's proper motion is well known, and that's the dominant cause of the rapid scintillation. So this was an interesting result, and it actually gave us confidence that even with a single measurement, one can actually infer the presence of multiple screens. And this exercise was, it took a while to get the techniques right. But I think now that we know, we want to repeat this exercise for many more pulsars. We already have some data on the pulsar 0329 plus 54, and we're also planning more of these in the next couple of years. So that's just an interesting piece of work on this 1508 plus 55. Just a few other things about this particular our VLBI. This is actually not a VLBI. I mean, we just used a baseline, but we did not do a real VLBI in the sense of the word. But it's an interesting technique to apply to pulsars. And this is not certainly, we were not the first to do it. There have been earlier examples which are actually cited here. So there have been examples of such measurements between, for example, the UT Radio Telescope and telescope in Australia in 1968, and then also in between Jodrell Bank and some other places. So certainly not the first instance. And what is interesting about our experiment is that the 10,000 kilometer baseline is somewhere between what has already been attempted. Previous experiments have all used a few hundred kilometers to maybe about 3,000, 4,000 kilometer baselines. I think the longest one was between UT and Australia, which was about 8,000 kilometers. But the 10,000 kilometer baseline is not as long as, for example, Earth space baselines, which are typically 100,000 or 200,000 kilometer baselines, like the radio astron baselines. So we are somewhere in the middle sweet spot. So we are neither fully resolving the scintillation nor completely unresolved. So I think and in particular, I think we should appreciate the fact that we can actually do this for many other pulsars with the GMRT and ARO, because the bands overlap, and it's a nice 10,000 kilometer baseline. So I think there's a lot of potential to unravel the scattering screens and their locations for many other pulsars, especially the northern pulsars, which ARO can see all the time. So, with our particular measurement, we rule out a fully isotropic scattering and also a strictly 1D scattering, because for fully isotropic scattering, one would expect the scintillation timescale to be similar to it would not be very different from the scintillation speed, the delay, whereas the cross correlation coefficient would not be so low if it was a completely 1D scattering. So so our measurements rule out both extremes. So what we infer is that it's actually a 2D screen or two 1D screens, which is what actually the latter is what our measurements favor. And it would also be instructive at this time to just recall the Briskin et al. Result. Many of you may or may not be familiar with it, but it's just sufficient to say that the Briskin et al. Measurement would still be fully correlated on the GMRT ARO baseline, because that was a fantastic 1D correlation. And so that this is just for context and just to appreciate the fact that what we have detected is indeed 2D scintillation. So this is just a quick overview of the work that we did for 1508 plus 55. And I see a lot of potential for further such observations in the future, especially with the GMRT and ARO. And the ARO has a dedicated program for observing pulsars for scintillation. So I'm still collaborating with a lot of people at CETA, and of course, Whaley Penn is one of them. So, so the topical summary, I'll just leave this slide here, just to say that also there is an update on the measurements of 1508 plus 55. Some fantastic work done by Tim Sprenger this year. Earlier this year, he published a paper based on Effelsberg observations. There have been some intriguing phenomena which have occurred with 1508 plus 55, and we have lots of data with the GMRT and also with Effelsberg, some simultaneous data. So we will probably be able to repeat our analysis on this slightly shorter baseline between GMRT and Effelsberg to fully understand what's happening with the pulsar. So, so with that, I'll just move to fast radio bursts. And again, here the idea is that we use the GMRT as a fantastic follow-up instrument to study FRBs, because as I mean, different telescopes have different strengths, and certainly the strength of the GMRT is that it's a fantastic follow-up instrument because of its excellent sensitivity, its ability to track a region in the sky, but not a fantastic survey instrument. There are other instruments which do surveys better, like CHIME, for example. And so I think every telescope should actually use its strength to its best advantage. And I think at least what we are doing with fast radio bursts is exactly that. So, of course, FRBs, again, a very hot topic. Everyone in the world knows, at least within the astronomy community, what FRBs are. So I don't have to give a great introduction to it. But just for completeness, we all know that initially there was some confusion about whether they were indeed extragalactic, but I think now that question is settled. So progress in the first decade after 2007, the Lorimer burst was indeed very slow. But I think with the coming online of CHIME and ASKAP, there has been an explosion in the numbers in the last 5 or 6 years. And now, of course, besides FRBs, we also know repeating fast radio bursts, and more than 100 such repeaters have been discovered till date. So that's just a quick background on fast radio bursts. And I mean, it's important to appreciate why FRBs are important and why everyone is jumping on the FRB bandwagon. I think FRBs are still a mysterious class of objects. We still don't know whether they are like magnetars, or whether they are like pulsars, or whether they are completely different class of objects which unknown physics, where unknown physics is operating, which we haven't figured yet. But I think it's interesting because when we keep on observing FRBs, we collect a larger sample of FRBs will be the first step, and especially localizing them is the first step to understanding their origins. And since the first repeater localization in 2017, now we have localized many more such FRBs. And it's, of course, clear that all the localized FRBs are extragalactic, except, of course, there is one galactic analog. So it's still not clear whether the connection can indeed be made. But I'm talking about the galactic magnetar, the SGR 1935. So FRBs are now being talked about as being used as probes for studying the host galaxy ISM, the intergalactic medium, and also the Milky Way. So you can also use FRBs as probes, not just as local probes of the host and the Milky Way, but also as probes as cosmological probes, and to also study the intergalactic medium. So lots of promise for rich physics there, emission models, burst properties. There are also empirical relationships which you can derive from the data, statistics, just trying to understand the full and map the full landscape of what's actually happening with FRBs. So so as I just coming back to why the GMRT is a fantastic instrument for FRB studies. As I said, I also motivated this to some extent earlier on, that we have almost seamless frequency coverage going from 120 to about 1460 megahertz with small gaps in between. And the flexibility of the GMRT is that it can operate as a single array. It can operate as double or triple subarrays, multiple subarrays, each subarray with observing at its own frequency band. So you have multi-frequency, multi-subarray observation or multi-band observations. You can also simultaneously observe in an incoherent array mode. I'll come to that later on in a few slides. I'll tell what this IA and PA are. You can also do coherent dedispersion. And then you can also simultaneously record interferometric visibilities. And besides, you can also now, it is possible to also record baseband beams. So and it gives you a lot of flexibility in what time and frequency resolution you want to choose, and whether you want full stokes or total intensity data. So it's a very versatile, very flexible instrument. And its ability to track a region of the sky from rise to set is perhaps its greatest asset, because that's how you can actually look at a target an FRB for a very long time. And that's precisely the fashion in which we study FRBs. We don't search for FRBs. Also, there is also an ambitious program to do transient search in a commensal fashion. But what we do is that we look at CHIME FRBs, especially CHIME repeaters, and we keep observing them. For example, if the CHIME localization is very poor, then you don't know where to look for. That is when you use something called the incoherent array. Actually, there is a typo here. The incoherent array should be called IA. So the incoherent array is where you actually add the intensities from each antenna and form a beam. And the delays are adjusted so that the beam is actually looking at one region in the sky. And here the beam width, of course, the beam size is the size of the primary beam of the antenna. And the sensitivity is square root of antenna times the single antenna sensitivity, right? So square root of n times more, actually. And it is actually square root n less sensitive than the PA. What happens in the PA, or the phased array beam, is that you actually add the voltages from each antenna, phase them up, you adjust for the phase delays, and then add the voltages, and then square it to get the intensity. So here, the beam is much narrower, because it's like having a single large dish, and you can choose to add as many antennas as you want, depending on your observation. You can add 10 or 15, or you can add the entire array of 30 antennas. And here the beam size, of course, is smaller, but it's also much more sensitive. So there are two ways of doing this. And I said, for example, the FRB that CHIME has just detected, and if it's known to be repeating, is only localized coarsely. You know exactly which region of the sky to look at with some large error, and that error is actually, the CHIME beam is actually well matched with the GMRT beam. So if you roughly know where to look for, you can point your telescope, you can record the interferometric visibilities. At the same time, you can also record the incoherent array beam data. You don't know where exactly the FRB is located, so you probably don't want to do a phased array observation. So the advantage here is that the incoherent array, as I said, is a wide beam. The beam width is as large as a single dish beam itself. And that's what we demonstrated, for example, in the observations of R3 or repeater FRB 2018-09-16B. What we did was, of course, at the time, it was already localized. So we actually recorded the IA beam beamformer data. We look for the bursts, and we know exactly when a burst occurs, we know what timestamp it is. And therefore, we go back to the visibilities and use those visibilities to get an instantaneous image of that burst. So this is a proof of concept, meaning that if you actually observed an FRB candidate, which is a repeating FRB, and you don't know where it is located, it's not well localized, you can use the IA beam to detect the bursts. And then based on that, you can actually go back to the visibilities, image the data, and localize the FRB. So this is, arc-second localization of FRBs, repeating FRBs. And this was actually done as a proof of concept with R3, but we actually demonstrated this also for another repeating FRB, again, very interesting repeating FRB, which is 2020-11-24A, or now called R67, the 67th repeater. So if you remember last year, sometime in late March, there was an ATEL from CHIME saying that there is one particular FRB, this 2020-11-24A. Not the first time it was seen, it was also seen earlier, but suddenly it had turned into a very active state. And it was showing a very high burst rate of the order of 5 per hour. And these were bright bursts, typically a few Jansky millisecond fluence levels. So, once this ATEL was out, we thought, okay, this is a perfect target for localization. It had not yet been localized at that time. So we did exactly that. The core's position was known. So we trained the telescope on that particular location. And we had the IA beam as well as the interferometric visibilities. And that allowed us to localize. Of course, by the time we localized, other people had also successfully localized. But this is just telling you the best way to use the GMRT for quick, rapid follow-up science. So once, of course, the FRB was localized with a particular observational setup, we also had multiple bursts because these were all bursts which were detected in the IA data. It is less sensitive, but nevertheless, bursts were detected. And of course, the visually identified dispersion measure was well within what CHIME had already cited. And we had the brightest burst was about 110 Jansky millisecond, which was what enabled us to localize it with arc-second precision. And there were lots of other bursts. I think we had a total of about 48 or 50 bursts, which allowed us to also do some statistics. So also we detected persistent radio emission and with a flux density of about 0.7 plus minus 0.1 millijansky for two of the brightest bursts, and the position sort of coincided. And we put out an ATEL, but of course, by the time many people had already localized, so we still have to think about putting out a publication for the localization. I'm not sure if it would make sense now, but nonetheless, I think this is just to demonstrate the fact that the GMRT can actually be used in a certain way to maximize the science output. So this is just the zoo of the gallery of the bursts. We detected 48 bursts in total, and you can see all kinds of rich morphology here, sometimes multiple components, some sort of sad trombone, and one of them with a drift, with the first component with no drift, second with the drift. So all sorts of structure that can be seen, and there's also a double horn structure here. So a variety of bursts, and as all FRBs, every single burst is an intriguing burst. I mean, every burst is interesting in that sense. So so we looked at some of the burst properties. Especially, it's now known that this R67 has wider than usual bursts. I think it's probably among the ones which are actually the widest bursts. So the burst widths are actually quite wide, and we define the burst width by going to what is called an equivalent width, where you simply compute the fluence and distribute that fluence in a boxcar window, and the width of that boxcar window is going to give you what is called the equivalent width. It's just a different way of defining. CHIME, I think, defines the equivalent width in a slightly different fashion, but as long as we have our definition, it's okay. So there's also distribution of widths, and you can see the mean width is about 18 millisecond, and that sort of actually includes the 2 millisecond intra-channel dispersion. We have 100 kilohertz channels. So within the 100 kilohertz channel, there's a 2 millisecond dispersion time scale also. But then even then, I think the width is on the larger side, because you can actually see that there's a tail for the gamma distribution, which goes sometimes up to 40 milliseconds, and these are equivalent widths. So so we actually found that this particular FRB has very wide bursts. And it's also seen at L-band, for example, with Effelsberg, where also Hilmarsson found that the burst widths are actually larger than usual. So although we detected the burst in the IA mode, which I just want to remind is the less sensitive mode of observation, the PA would give you, or the phased array would give you much more sensitive data. But at the time, since it was not localized, we only had the IA data, and we could already derive a burst rate function with a slope of about minus 1.2. And this minus 1.2 is shallow, and it's close to minus 1.5, which is actually a very well-known selection effect for flux-limited surveys. And there are lots of experts who do statistics on FRBs in type A, so I don't have to dwell on this. But anyway, we also found that this particular observation was actually very incomplete. We only detected a small fraction of the bursts that would be above fluence limit of 7 Jansky millisecond. So we were actually missing a very large fraction of the bursts given this particular burst rate function. And that was again down to sensitivity. And what is shown in the bottom left is, of course, the revised picture from FAST, which is, of course, extremely sensitive. And you can see a clear bimodal distribution in the burst rate function. And of course, what we were detecting is only this power law part of the burst rate function. So we also looked at waiting times. We had multiple scans. There had to be breaks between the scans because every 30 minutes or so, we had to rephase the array because the ionosphere is very different across the whole array. So every so often, one has to go on a calibrator, rephase the array and come back. And so there are gaps in the scans. So different scans had a different number of bursts. So we also looked at whether there was any modulation in the arrival time. And that analysis turned negative because it looked like there was no apparent modulation time. The modulation time one would expect, for example, if an FRB is in some kind of an orbit, when it's because of Doppler effect, for example, there could be a bunching of bursts when it is coming towards us, and could be appearing to be more spaced when it is actually the orbit is going away from us, or if something else is happening, there is an intrinsic modulation in the burst, the way the bursts arrive. So we did an analysis on the waiting times, and the waiting time, of course, it appears that it is actually the underlying process is Poissonian, and so we get an exponential waiting time, the mean waiting time of about 3 minutes. And this is not unexpected for a single observation. In a single observation, of course, obviously, you would always expect it to behave in a Poissonian fashion. And clustering is, of course, seen when you observe for much longer across multiple epochs. And Lee et al. Also with FAST, they observed waiting times, and because of their extreme sensitivity, they were able to see that there was a sharp bimodal distribution, but they still ruled out that this is certainly only stochastic, and there is no short-term periodicity at work, which gives rise to this kind of waiting time profile. And what we are, of course, looking at is the waiting time distribution shown in the right is, of course, what is shown in this this green box here. So we're just looking at the tail of this log normal distribution, and therefore it looks like it's an exponential. And of course, that's obviously because of the sensitivity. We only use the IA beam here. And what is more important is that we also looked at the scattering and the scintillation, and what is shown on the left is a particular burst from GMRT band 4, where you can clearly see what looks like a scattering tail. And the Effelsberg L band shows very clear scintillation. You can see all these banded structure from L band data, Effelsberg L band data. So there's both scattering and scintillation, but what we found is that the two are actually coming from two different sites. For example, the scintillation is expected to behave with the lambda to the 4th power as a function of, so at different frequencies. We observed at GMRT band 4, where the scintillation is sort of barely resolved at the lower end of the band. And Effelsberg clearly resolves the scintillation because at L band, the scintillation bandwidths are much larger. And what we also found is that the scattering time scale for the scintillation time scale from the scintillation bandwidth at 1 gigahertz is about 0.3 microseconds, and that translates to about 1.5 microseconds at the GMRT band 4. So what you see as scattering is certainly not entirely contributed due to the scintillation. The scintillation alone cannot explain that. So there is something intrinsic that's going on. Now, it's still an open question whether it is actually scattering or intrinsic burst structure, and that's a relevant question. And one of my students is actually looking at some of the more recent observations of R67 with the PA and also some baseband data, where the higher time and frequency resolution will allow us to address those questions. So what we also find is that at least in this particular FRB, and Robert Main is, of course, an expert on scintillation. And what we find here is that similar to the case where earlier it was detected at least in one FRB in the GBT survey, there are actually two screens. One screen which is located at the host galaxy, and the other which is at the Milky Way. And the scattering is actually local to the host. The host galaxy, the circumburst medium is actually causing the scattering. And it's the Milky Way screen, which is either at 400 parsec or 2 kiloparsec, which is causing the scintillation. And this was actually the initial analysis. And now we know that there is actually evidence for the Milky Way screen being at 400 parsec, being the cause for the scintillation. I mean, we could also verify that the scattering is actually very likely local to the host, because if you look at the NE 2001 model, this particular line of sight is highly underscattered. So it clearly meant that the scattering was indeed local to the host galaxy. So as I said, there's a two-screen model. The scattering comes from the host, the scintillation from Milky Way, and we've been able to refine these measurements. Now there's also an annual modulation of the scintillation, because this 400 parsec screen is so close to us that it is sufficient to modulate the scintillation timescale very well. And scintillation timescale is something that we have measured for the first time in any FRB for this particular one. This was possible because of the prolific burst rate. The bursts came so often that we could actually measure the scintillation as a function of time also. And the time scale ranges from 8 to 13 minutes at the GMRT band 4 and Effelsberg L band. And there's another FRB which is now repeating in a prolific fashion, where also probably we'll be able to do a similar thing. And I'll come to that in a moment. And that's what I was talking about. So this particular FRB, which is now being observed by almost every radio telescope so often, especially in the last couple of months, is we also observed it with the GMRT approximately a month ago, and we've detected more than 100 bursts, and we put out an ATEL, of course. And this work was chiefly driven by a couple of graduate students, young, bright graduate students that have taken the lead on this particular proposal. And what you see here is just a gallery of the bright bursts from this particular observation. Here, of course, it was already localized, so we have the PA beam, so very sensitive observations. And we also have baseband data from the same observation. So we will actually be looking at some of the bursts in great detail, especially to study from the point of view of scintillation and scattering. So that's just a topical summary. The GMRT, as I can't emphasize enough, is a fantastic instrument if you want to follow up FRBs, especially, we've been very productively following up CHIME repeaters with the GMRT. I think that's partly because of the fact that the beam sizes are well matched, and we're also in the northern hemisphere. So most of what CHIME sees, we'll also see. And the ability to track FRBs from rise to set and observe them for longer durations also gives us the advantage. And just giving a quick summary of the three different FRBs, R67, where of course I showed results from our published papers. We infer the presence of two screens, one at the host and one the scintillation caused by the Milky Way. And R3, which is also a very interesting one with a 16.35-day activity period. And right now we have lots of data with analysis ongoing and observations in this particular, the current cycle also. And right now our focus is actually on polarization. So we have plenty of data with full Stokes, so we can actually study the polarization properties of R3. And as I said, the last slide that I showed, we have detected more than 100 bursts in a 2.5-hour observation, and we are putting in more request time for requesting more observations, regular monitoring of this FRB with the GMRT. So if it continues to be so active as it is now, I think we'll have we'll have lots of data to do very good statistics on FRBs in general, and this one in particular. So, with that, I'll move on to the next topic, which is the instrumentation part and what we've done at the GMRT to enable VLBI, and where I played the leading role here. So,
sorry, Visweshwar, we still have about like 10 minutes. So
yes,
could you please try to,
I can finish in 10 minutes. Yes,
okay, sounds good. Thanks.
Thanks, Shushan. Yes. So, I'll talk about how we have actually enabled VLBI with the GMRT. So, of course, I don't have to introduce VLBI because we have an expert audience there at Taipei who does a lot of VLBI, especially with the Event Horizon Telescope. But I think it's important to appreciate the fact that VLBI is challenging for many reasons, especially at low frequencies, because of the way the ionosphere behaves and how it distorts the radio signals. There are, of course, many continent-sized VLBI networks, but you will see that in none of these GMRT has there's no picture here where the GMRT actually features. So we've sort of not really focused on VLBI so far, and that's because we were primarily we are positioned as an imaging interferometer. But the challenges here is that in any VLBI, there is no coherent phase relation between the signals. Each station has its own clock, its own local oscillators, frequency standards, and real-time correlation also is a luxury. I mean, there's currently only the eVLBI is capable of doing that. And we also have non-standard polarizations, the data recorders are different, native formats are different, and all these are challenges, but those are all surmountable. Those are really least of the concerns. So as I said, the GMRT is always being positioned as a synthesis interferometer, not really designed for VLBI. It's always a challenge with an array like the GMRT. And earlier we used a rubidium standard, so the clock would drift on intercontinental baselines. And in the past, there have been some attempts to do VLBI, not very successful, especially with Europe and Australia. But also the limited bandwidth that the earlier configuration gave and some non-standard sampling rates, such as 33.33 megahertz, also did not make it very VLBI friendly. And also the fact that at L band, we have a linear polarization instead of circular is also another stumbling block. But with the upgraded GMRT, as I said, and this is sort of slightly repetitive, but it's sufficient to appreciate the fact that these wide bandwidths, 200 and 400 megahertz, allow us to actually pick regions within the band, which can then be used for VLBI correlation. So at L band, for example, the full 400 megahertz is accessible, and the full 400 megahertz is now basebanded. And within the 400 megahertz, one can, of course, choose whichever sub-band required for VLBI as required. And now there is also an active hydrogen maser, which provides reference, the LO reference and the clock. And the baseband recording has been enabled. And the heart of this whole instrumentation thing is the baseband as well as the post-processing for VLBI. So as I said, we have non-standard bandwidths like 100, 200, and 400 megahertz, and we have to condition the signal to VLBI ready bandwidths of 2 to the power n megahertz. And then there's also subsequent sample rate conversion and re-encoding. So I'll probably skip this part. It is sufficient to appreciate the fact that there are 3 possible baseband streams at the GMRT, and the most versatile one is this mode 3, which is likely to be the workhorse for our VLBI, and which is called the PASV, or the phased array spectral voltage. So instead of squaring the voltages to get the intensities, which is what your PA beam would give, you capture the voltages right before the detection is done. So it's giving you the voltages, but of course it's in the form of a spectrum. So every few samples is FFT'd and dumped as a spectrum, as a complex spectrum, and that's what we are grabbing and writing into a file. So once we have the PASV baseband, well, if you don't have the PASV, which is if you just directly Nyquist sample the 100 megahertz GWB baseband, then you can actually filter the relevant section by doing an FFT and putting a spectral weight to extract the required band. But with the PASV, it's already in a spectrum. So all you have to do is just put that spectral weighting function to extract the relevant band. And then you do an IFFT. And now the actual signal bandwidth is much smaller than the 100 or the 200 megahertz. It may be 16 or 32 or 64 megahertz. And therefore, you have to actually do a sample rate conversion, because at this stage, it is already super sampled. So there's a sample rate conversion, which is based on a simple sync interpolation. And then the 8-bit data then re-encoded to 2 bits and written into a VDIF file. So now it's ready for VLBI correlations. So so this is just a picture showing how the filters can be fit. So these are all done in software, of course. When I say filters, it's all software. So you can actually have multiple subbands, but there is some condition on where these filters have to be put, because we are actually doing bandpass sampling to get the to shift the bands to the baseband. Now, of course, what you show or what you see on the left is a before and after filtering. The power level is kept the same across the band. So the area under the curve is the same, just to ensure that the bit occupancy is not affected because of doing this filtering. And what you see on the right is, of course, the histogram of the samples, the 2-bit samples. So you have 4 levels, the 2 polarizations. And finally, we use the histogram to see whether the chain has worked correctly and whether the power levels are appropriate for correlations. So, so we did our first fringe test experiment with the EVN on 14 February, approximately 10 months ago. And we detected fringes right away. And what you see here is just the GMRT to some EVN telescope fringes, right at 0 lag, of course, adjusting for very minor clock delays, and very promising result, very promising first attempt result. So what you see here now is the UV coverage with and without the GMRT on the left. And you see that the inclusion of GMRT has actually increased the baseline length. Now, it's important to appreciate the fact that the GMRT is not, of course, giving the longest baselines to the EVN, because we have telescopes to, for example, Shanghai, which give even longer baselines. But I think the GMRT has an important role in the sense that it is extremely sensitive at L-band. Given these other telescopes, it's adding a lot of sensitivity, and it's also adding intermediate baselines, which actually, helps to fill the UV coverage. The UV coverage is enhanced, and you get much better with high fidelity images if you want to do imaging, of course. And of course, what I'm showing here is the image of a particular calibrator, well-known calibrator radio source, 3C454.3, and on the left is without the GMRT. On the right, you can already see some kind of a jet core structure enabled by the longer baseline supplied by the GMRT. So this is just an example of, this is just the result of this particular fringe test run. But of course, my own interests in enabling VLBI is to be able to do VLBI scintillometry, and I'm still working towards getting some of the pipelines ready. So hopefully, in the near future, we'll be able to do, at least GMRT Algonquin real VLBI instead of just the intensity cross correlations that I showed earlier. So in summary, GMRT is now, officially a VLBI ready telescope, and we have the full VLBI signal processing pipeline in place, and we have successfully demonstrated with EVN, also with Parks. And we, although I did not show some of the detailed results, we observe that the phase and the fringe stability that we have achieved is excellent, and it's more than sufficient for doing real VLBI. And we're still looking at some of the subtle systematics and investigating whether it is something intrinsic or something due to the ionosphere. Analyses like those are actually in progress, and we should be able to wrap them up shortly. We are actually trying to do some fringe tests in P-band and at band 4 of the GMRT. Of course, band 4, there is some overlap with Meerkat. And P-band, there are only a few telescopes in the world which can do VLBI, so we are looking to do those as well. And one potential development, and I think this will be made official shortly, is that we are also becoming an associate EVN member, which means that the GMRT will actually participate in regular EVN observations. Right now, at the moment, only in L-band, of course. So as I also said, let me repeat that the GMRT, besides providing great sensitivity, will also fill an important gap in the UV coverage, and especially in improving the fidelity of the image at those mid scales. So with that, I'll end the talk here, and thank you all for your attention.
Okay, thank you, Visweshwar, for the very interesting talk. So are there any questions from the audience? Mayank, please.
Hey, Visweshwar, one quick question. So what's causing the scintillation at 250, 125 parsec? Do we know what's the cause of that scintillation? Is it just in the first in the first part of your talk?
Okay, fine. Let me just go there. Are you talking about the B1508 plus 55 pulsar?
Yes.
So the current picture is that there are 2 screens. So there are actually 2 screens. One screen is close to 125, 130 parsec, and that's well known. and that's causing this main scintillation arc in the secondary spectrum. There is a second screen which is actually not seen with any single dish. But what has been observed is there is recently, like about a couple of years ago, there was a change in its scintillation properties. It suddenly changed from weak scattering to strong scattering. And so there, there is a different picture, which is actually there are two screens, and the screen behind is undergoing, the screen behind is undergoing some change. And the 125 parsec screen is actually able to act as a lens or an interferometer to look at the screen further behind. So that's the picture right now. So your question is what causes the scintillation?
Yes.
There are actually features on the screen itself which cause multiple images.
Okay.
And that causes those multiple images. Then the wavefronts from those multiple images interfere at the observer, and that's what causes the scintillation. This is the this is a good picture to understand scintillation.
And like, what's the screen made of? Is it just electrons, or do we know, like, is it because of some dust cloud or something?
Okay, so typically, so the current picture, and this is something that Whaley Penn has proposed, and it's gaining more and more currency, is that earlier the picture was there was just a turbulent medium, and the turbulent medium is actually not good enough. There are many physical impossibilities with the turbulent medium that can actually cause scintillation, like, for example, this highly anisotropic scattering. So that picture has been challenged now, and now the picture is that there are actually these very thin reconnection sheets. So these are sheets which are actually held in place by magnetic fields, and they may be underdense or overdense with respect to their surroundings. And they're actually highly inclined to the line of sight. And those would actually cause the scintillation in a majority of the cases. So they're actually plasma.
There will be a colloquium in February by Dan Steinbrink, who is again a leading expert on scintillation. So stay tuned.
Yeah.
Okay, thank you.
Any other questions? Yeah, Satoki-san, please.
About the VLBI part, maybe I missed, but you use the VLBI use the phased array only for the central 15 antenna or whole array?
That's a very good question. So in our VLBI, we have used only the central square because we have better control over the ionosphere. There is nothing that prevents us from using the full array, but then the problem is that you would have to rephase the array very often, and that would add considerable overheads. But currently in the experiment that we conducted, we added only the central square antennas because they're all very close and within 1 square kilometer. Yeah.
I see. So that the sensitivity wise, what's the size corresponding to the one telescope? Like 100-meter telescope corresponding to 100-meter telescope, or?
Okay, so each telescope is 45 meter. So if you have a phased array, for example, if you have 10 dishes, then it's like so the sensitivity is n times the 45-meter telescope. So I would say in terms of area,
yes.
It is. I think it will be more than 100-meter telescope in terms of sensitivity. Yeah.
Oh, okay, that's good to know. Okay, thank you very much.
So it's the biggest VLBI telescope in the world after Arecibo collapsed. It's still the biggest now.
Yes.
Yeah. Okay. Any other questions? If not, let's thank Visweshwar again. So thank you. Happy holidays, and talk to you later.
There was a question by Tang Tang. Maybe you just want to get that one.
No, I want to say thank you. Yeah. Thank you.
Okay, thank you.
Thank you very much for your attention. Thank you, everyone.
Okay, thank you. Happy holiday. Goodbye.
Goodbye. Happy New Year.